Your program looks fine. No crashes, no errors, no warnings in the console, but leave it running overnight and something strange happens. It starts slow. The OS starts killing processes, or worse, the server just falls over at 3 a.m. and nobody knows why. The culprit is memory that was allocated and never given back, a memory leak. It does not announce itself. It accumulates quietly frame by frame until the system has nothing left to give. In this video, we will dissect exactly how that happens and what you can do about it. Here is the core paradox. Modern programs do not manage memory directly. They ask the operating system for it and then hand it over to a runtime or garbage collector. So how does memory leak at all? The answer is deceptively simple. Memory leaks when your code holds a reference to an object that it no longer needs. The garbage collector cannot free memory it thinks is still in use. The allocator cannot reclaim a block that was never released. Even in managed languages like Java or Python, a live reference is a live reference. The collector sees it and walks away. When your program needs memory, it calls into the heap allocator. The allocator carves out a region, returns a pointer, and records that the block is in use. In C, that is malloc. In C++, that might be new. In Java or Go, the runtime does this invisibly. Every allocation has two parts, the request and the eventual release. In unmanaged languages, the release is your responsibility. In managed languages, the garbage collector handles release automatically, but only when no references remain. The heap is not infinite. If you keep allocating without releasing, the heap grows, the OS pages memory to disk, and everything slows down. Reference counting is the simplest form of memory management. Every object tracks how many things point to it. When that count reaches 0, the object is freed. Python uses this model. Swift uses it for its automatic reference counting system. The problem is cycles. Object A holds a reference to object B holds a reference back to object A. Both counts stay at 1 forever, even if nothing else in your program can reach either object. They are an island, completely isolated, but the allocator can never reclaim them. This is a reference cycle leak, and it is extraordinarily common in GUI code, observer patterns, and parent-child tree structures. Managed runtimes like the JVM and the .NET CLR use tracing garbage collectors to catch cycles that reference counting misses. The collector starts from a set of root references, which are things like local variables, static fields, and thread stacks. It traces every reference reachable from those roots. Anything it can reach is live. Anything it cannot reach is dead and can be freed. Cycles between unreachable objects are collected because neither object is reachable from a root. The key insight is that the collector defines liveness by reachability, not by reference count. But this shifts the burden to the developer. If you accidentally keep a root-level reference alive, everything that root can reach stays in memory forever. The most common real-world leak pattern is the forgotten listener. You register a callback, an event handler, or an observer. Somewhere in your codebase, a static list or a singleton keeps a reference to that listener. When the object that registered the listener is done, the listener still points back to it. The singleton keeps the listener alive. The listener keeps the original object alive. Nothing gets collected. In Android development, this is called a context leak. You pass an activity into a background task or a static field. The activity is supposed to be destroyed when the user navigates away. But the background task holds a reference, so the entire activity, its view hierarchy, its bitmaps, all of it stays in memory. Caches are another major source of leaks. A cache is deliberately keeping objects in memory for faster access. But a naive cache with no eviction policy grows forever. Every object you cache stays cached. In production systems, this is often the largest single contributor to memory growth. The fix is bounded caches with explicit eviction, by size, by time, or by access frequency. Java provides weak hash map where the keys are weakly referenced, meaning the garbage collector is allowed to reclaim them when nothing else holds a strong reference. When a key is collected, the entry is removed. This pattern lets you cache objects without preventing their collection, though it requires careful design to avoid stale data. Closures and anonymous functions capture variables from their enclosing scope. In JavaScript, a closure over a large DOM element prevents that element from being garbage collected even after it is removed from the page. In Python, a lambda that captures a large data structure holds that structure in memory for as long as the lambda exists. The lambda may be stored in a list or a dictionary that outlives the original context. These are called closure leaks. They are particularly insidious because the leak is invisible in the data you think you are storing. You inspect your cache and see 100 small lambdas. What you do not see is that each lambda holds a reference to a megabyte of data from the context in which it was created. Practical tools for finding leaks fall into two categories: heap profilers and allocation trackers. A heap profiler takes a snapshot of everything currently allocated, annotated with the call stack that allocated it. Tools like Java Flight Recorder, the Instruments app on Apple platforms, and Valgrind on Linux all work this way. You take two snapshots, compare them, and look for objects that grew between snapshots without a clear reason. Allocation trackers record every individual allocation as it happens. This is more expensive at runtime but gives you a precise trace from the moment the leak began. In Python, you can use the trace_malloc module. In Go, the pprof package gives you both heap profiles and allocation traces at low overhead. Prevention is more reliable than detection. Establish ownership rules. Every allocated object has exactly one owner. When the owner is done, it frees the object. Use smart pointers in C++. Unique pointer for sole ownership, shared pointer when multiple owners are required, and weak pointer when you need a reference that does not keep the object alive. In garbage collected languages, prefer scoped lifetime patterns. Keep references local to functions. Avoid storing references in long-lived containers unless you explicitly manage their removal. Audit every place you register a listener or callback and ensure there is a corresponding deregister call when the lifecycle ends. A memory leak is not a runtime failure, it is a design failure. Catch it in review, not in production. Memory leaks are silent, they compound over time. A program that leaks a megabyte per hour is fine in testing and catastrophic in a month of production. The underlying cause is always the same, a reference that outlives the intention of the programmer. Whether that is a reference cycle in Python, a forgotten listener in Java, a closure over a DOM node in JavaScript, or a raw pointer in C that was never freed, the effect is identical. Memory that the program can no longer use but that the allocator can never reclaim. Understand your runtime's memory model, profile before you ship, give memory back when you are done with it. Thanks for watching.